Can you hear me? Hello? Hello?
Yes, sir. Yes, sir.
Screen is visible?
Yes, sir.
Audio is running?
Yes, sir.
Video? Because
Yes, sir.
Saurabh complained that last time he forgot. You didn't tell me. Hmm. Well, I was talking about vector lattice. Partially ordered, you have vector space. You can take X or V, whatever notation you take, or X. On that you have partial order. And which is compatible with these two operations. This by compatible I mean that I explained last time that in Alipantis Barkinsa you look at the top of page 67 that if you have this, you greater than equal to V because you have a relation here. I should say even need to use that. Usually you should have this, but often we write this, but it is not another relation. It is just another way of writing this to indicate this. Y greater than equal to X means X less than equal to Y. This relation. Relation is only one relation, but this is just a alternative notation. This is a notation. So U greater than equal to V means actually V less than equal to U. That implies U. So V plus W less than equal to U plus W for all W belongs to V. There they have taken E, that doesn't matter. Usually it should be V or X. Okay, so this is means compatibility between order and vector addition. And about the scalar multiplication, V less than equal to U implies that alpha V for all alpha. Yeah, it is over real. This vector space over R. Over R. So it makes sense. Okay, so this is compatibility between this relation and scalar multiplication. Then, okay, now you see that this is a very big concept. It is not the usual positive elements on that. If you have this, okay, now look, this 0, 0 we use for the 0 vector of V as well as 0 for of R. But from the context, same notation used. From the context, it will be clear. Some people use theta for 0 vector this, but that is not required. It will be the same notation, but from the context, it will be clear that what you are using for. Now, look here, you have V a vector, that partially ordered vector space. That is called the partially ordered vector space, should be the proper name, but people usually called ordered vector space. Ordered vector space. Okay. Now here you have a V in V and also 0 vector. Now look, I have given the order. The partial order, you should make sure that they need not be comparable, any two elements. Okay. Two elements like here. These two elements are not comparable, but it is a partially ordered space. Okay, so that what I'm saying that they need not be comparable. But suppose you have this. In other words, I told you the alternate notation, often we use alternative notation. Then it is called a positive vector. And on the other hand, if you have this, then it is called a negative vector. Okay, so this makes sense. Okay, if it's not comparable, that's fine, no problem. But if you have this, you call it positive vector. If you have this, you call it negative vector. So that means if you have this ordered vector space, so I have the concept of positive vector and negative vector. Positive and negative vector. Okay, right. And now they are talking about vector lattice. Basically, model is always Cx, or if you can even think of Bx. X is a non-empty set. Don't confuse with the vector space. Here I am taking V vectors. Px means set of all bounded functions, real valued bounded functions on a non-empty set X. And here you don't need topology, but here you need topology. Okay, so vector lattice. First of all, vector lattice. Since they are telling briefly, I am explaining that what I mean. Suppose you have X a subset of V, non-empty subset. Okay, suppose you have it. Then now it is ordered vector space. So suppose you have this S, there exists, suppose whether it belongs to S or not, that is a different thing. Suppose there exists X belongs to V such that S look, this makes sense because I have this relation. Suppose you have it, you don't need to have it. Suppose you have it, then this is called bounded above, like in the real line you have done. Okay, and X is called, this is not here written, but I am writing in that. It's called an like real line, an upper bound of space. Okay, called an upper bound. Similarly, you can define least upper bound or supremum. Look, it will mean that if any other upper bound will be bigger than this, that means X is called supremum. First I'm writing a supremum, then I will say this is, it has to be unique. It's called a supremum or least upper bound if X less than equal to Y, whenever Y is an upper bound of S. So among the upper bounds of S, this is sort of minimum. That is called a supremum. But this has to be unique, because if you have two supremums, then by definition we will have this and this. And remember, this is a partial order. So it has to be x equal to y. So it has to be unique. Okay, it has to be unique. Similarly, look what you can do if I have this. Now look, suppose I have this. What I'm going to write, suppose there exists V such that X belongs to V such that, don't confuse with the usual order in R, this is this. Okay, so S is called bounded below and X is called a lower bound if, let's go with this file, it's called a lower bound. Okay, fine. Okay, and X is called a lower bound of this thing, and X is called a GLB or infimum of S. This infimum, in short, we write inf. In when you're talking about vector space and this, usually use inf sup. Previously it was called supremum. And here you write inf. Usually you do not use the term GLB or ULB. Whenever y, so this will be y less than equal to this, and whenever y is a lower bound. Okay, of this. So X is called this thing. In fact, for this definition, you need only a partial order. It can be defined any partial order set. You don't need a vector space. Okay, you don't need a vector space. That it should be clear. It should be clear that you just need a partial ordered vector space. I think last semester I did also. So this is called infimum, supremum. Now infimum also will be unique. Okay, if you have a bounded below. Now suppose S is only two elements. Now vector space you are having V, this scalar multiplication. Okay, now suppose you have two elements. But for every pair of elements, but be sure, first of all, let me notation on that suppose this, of course you assume it exists, sup of xy, this notation is this. This is the notation, sup of this. I'm not saying it exists. If it exists, the notation I'm giving. Some people call it in this case for two elements maximum and minimum of that. Okay, these are the notations, right? It's taking this. So these are the notation for two elements. So, and suppose now vector for each pair of elements, for each pair, for each s, that means whenever x these two exists, suppose exist for each s, each s means for any pair of this exist in this. Okay, that is given any pair of elements, supremum, infimum always exist. Then V is called a vector lattice. Actually, I want to give you the two versions of Stone-Weierstrass theorem. One is algebra version, other is lattice version. That's why I need this. V is called a vector lattice. Okay, V is called a vector lattice. Okay, so you have some algebra, you have basically linear algebra, but how do you link it with analysis and topology? That's the question on that. That eventually will link. Okay, right. This paragraph 67 you should read, and that vector lattice that I already said that unique. Smallest upper bound multiplied least upper bound. Okay, now it's called a vector lattice. Now these things A, B, C, D, I think here they have proved B. So that now look here first A, that thing. This I am leaving it to prove in this exercise. One proof they have given it. I think B. Okay. So look here. This. This is, remember that. So saying this is equal to minus. Look at a first, if you want to see whether it is correct or not, you see that Cx and Bx, where x has a topology, you can take R and you can take this thing in this. Whether they are true here. Look here, the functions, is the negations will come, so that here you see minus u, it makes in a vector space. Okay. Minus u, you should know in a vector, it means minus 1 into u. समझ गया? This is the scalar one, that and its negation minus 1. Minus u, look, this is infimum. This is natural expectation. You're replacing their negation, then you're taking infimum, then when you're coming back, it has to be minus. Okay, so this you should prove. Okay, basically, how to prove that? One proof you should look at that. In fact, while proving, they are using the notation fg, because these are, you should check how to prove here. You should have an idea that if you can prove here, you will be able to prove here. But if you can't prove here, don't expect you will be able to prove it. Okay, so that basically you'll have to prove this is less than this is less than this. Okay, similarly, you have other things that look how supremum B, look how they are doing. U supremum, and you are adding with supremum one vector. Then how it is coming? Basically, you are translating, you are not changing anything, so that it should be, and that is true. First of all, what should be your natural expectation? Look, this means this is supremum of this, and here is supremum. Basically, supremum we are translating by W. Here you are translating supremum of this by W, then it will be the supremum of the translates of this. This is a translate of U, this is translate of V. So that is exactly happening. Okay, similarly for, if you change this C, it should be this also. There are dual results actually. Okay, you can even use, if you can prove one of them, you can use A. A gives the relation from how to go to from supremum to infimum and from infimum to supremum. A gives a way, it's a road. It's a way to shift from sup to inf and inf to sup. So that if suppose if you result it prove any from sup, then a corresponding result will be true for inf by A. So that if you can prove this, it will be one of them actually you need to prove. Okay, right. And this is with the addition is coming. Now, if you do it, be careful. When you are doing this alpha scalar, it has to be greater than or equal to 0 if you want to maintain the equality, inequality, sorry. Right. So that here, alpha u phi, this is supremum. Here, basically, you're changing the scale. If alpha equal to 0, both sides will be 0. That's not a problem. So you need to assume alpha greater than 0. So that it is basically you are changing the scale. Nothing else you are doing. For all alpha. Alpha less than 0, you can do that. If you have alpha less than 0, then you take minus alpha greater than 0. Then you use this. And then you use A to get the similar result. Okay. So that you can do. Okay. So this is similarly, what about this? Sorry. What about this? I have not proved here, but I think it is must be some exercise. Let me see that. You should do this exercise. I may choose a short question in the major exam so that yes, it is in question 1 D. So make sure that exercise you will do page 77, number 1. They have given 7 parts, and it is here. It is part D here. There should not be any discrimination between the sup and sup and inf. Okay, if something is true for sup, it should be true for inf, and vice versa, and vice versa. Okay, it's a very wide thing. Many things together we can study in a giant structure like this. In measure theory, I do not think you will be given that. Measure theory, you will have that later on. If you do sign measure, then you have positive measure, negative measure, and the mixed measure, sign measure, that is called. Okay, there also you have this concept. Okay, so that you got this, the result you'll have to prove this. Now you will see that I'm assuming, of course, when I'm writing that, I'm assuming it's a vector lattice. And I'm assuming it is a vector lattice. Okay. Right. And now you see that you define U. So vector lattice, any pair of elements you have this. Given any pair of elements, I have this. This exists. That is the definition of vector lattice. That's how technical lattice. So suppose U belongs to V and 0 belongs to V. The way you did for Cx or Bx, then U plus is defined. Soup of this. Okay. Actually, I don't know how you defined, they have defined integral over that. Okay. Usually for, they do it for non-negative function. Look, in measure theory, first you come for simple function, integration. Simple non-negative function. And then it comes non-negative functions. And then NEAF can be written as this, that I will explain that. Two positive parts. Okay, this is called positive part, negative part, but both are non-negative functions. So you have the integral of this, you have the integral of this, the difference of their integral. If both the integrals, if both are not infinite, then this is the integral is defined. That is the help. Okay, so it is not something you're doing very abstract. Okay, so that you have this, then u plus this. So, and what will be u minus if you are defining inf u minus. This is the idea actually got here. for their functions. U plus, U minus. Okay. Sorry, I have made a mistake here. It is not like that. It should be always should be what? Minus U, but yes, they are defining this way, but I have defined this. Is it correct or that? Okay, go back to that. Okay, let me see that. Let me see that whether it is same thing. Okay, so that you see, first thing is this U, this minus U minus phi. Okay, so that U minus U, this minus, this is minus of this, so this is U, and this is V is 0, so this is 0. Okay, so this will be one minus will be here. समझ गया? Okay. Why it should be minus? Then the minus vector, it should be positive. U supremum you are taking minus U 0. You should check that. This is minus U, this. I think this is all right. Okay, right? It should be. You check that. These are things all, look, maximum of that. Okay. You check whether this is a positive. So that it should be this. And you check this is a positive thing. That you should check. Now, you look. So U plus is this. If you want to stick that. That's why they have stuck to the same thing. Minus U. Okay. Right. And then you can check that U will be this plus U minus. And here you define, if you had defined, this will be, you can check that this is defined like mod of that, mod U plus in real number, you check that just that is with the usual order. Okay, right? That should be that. So this is you are defining. This is called the, in measure they call it total variation. Okay, this is called the positive variation. This is called negative variation. In fact, I don't know you have been taught that, but I usually teach sign measure. Any measure, if you have sign measure concept, in this book also you'll find it. Then any sign measure, that is mixed measure, it can take negative as well as positive value. Then it can be, if you have sign measure, finite sign measure, only take finite values in that real number. Then it can be written as like difference of two measures. And then you have another measure. So this is called the positive variation of mu. This is called negative variation of mu. But those are both are positive measures. And this is called the total variation. If the teacher is not teaching sign measure, make sure that you read sign measure. In fact, you can read from that book I said, Bartle's book. It's a small book, but it's a very good book. Bartle was one of the leading measure theorists of the last century. Okay, so you can read Bartle's book, Sign Measure, because if you want to understand function analysis better, you will need there. I'm a little bit diverting, but I'm telling you, functionalism is born in two directions. One direction came from measure theory. It was before function analysis. though they are developing simultaneously. And another one, the Hilbert space that Hilbert did. But actually he was doing little L2. So this is the way it got developed, and that ultimately it became a big area, function analysis. Okay, but it came two ways. That's why if you want to understand function analysis well, you need to understand measure theory well, because function analysis many good examples, including so-called counter examples, come from measure theory. This one will help you when you are talking about spatial spaces like Hilbert spaces. But general function analysis, if you want to understand function analysis in a broader perspective, you must study measure theory well, particularly sign measures. Okay, now look here. Now look, so that you have a vector space V, vector lattice actually, lattice, vector lattice of this, so that U plus is this. This is very important. U minus, because I want to give the lattice version of the Stone-Weierstrass approximation theorem. So U minus is this. These are all you are defining. And this, after you have defined this, you can define this, but you can check that they're defining this. That exactly in the real line, what is this? This means either this bigger of this, right? Supremum of this. The same thing I'm doing, U and minus U. Okay, that's the natural definition. Okay, right? And here theorem 9.1, I'm not giving the proof. You can look at the proof, is very simple. That U is actually, you have defined, these are definitions. And then you can prove that U is this mod U. I have proved this way. Some people use this thing. I have defined this way. Some people take this as definition. But then they can prove this. And here, the infimum of that, it has to be 0. U plus, U minus. Okay. So this is the basic properties of lattices. Okay. And look here. So in that we have defined vector lattice, not only lattice, vector lattice. With relation to vector lattice, there is a concept of function space. I was telling last time and that actually my specialization is function space. That's why I work in function analysis, topology analysis, many things. But my area is actually function space. What function space means? So first of all, that the vector space will be of functions. Now look, the function space, here they are giving definition. Look there, page 68. In the middle, definition of function space. Function space is a big area. It overlaps many areas. Complex analysis, function analysis, topology, depending on what interests somebody. What is the taste of that? More analysis, then it will be particularly function analysis or complex analysis. And more topology, then it will be topology basically. It all depends on the taste. Okay. In fact, you can do algebra also. That will see that algebra function space. So a function space, first of all, that way they are defining, take X is a non-empty set and suppose L. That because you call it lattice, that's why L is a, depends on whether you are taking, if you have topology continuous functions, if you don't have topology, you are taking bounded functions. L is a vector space, that means linear space of real valued functions. not necessarily all, of real valued functions defined on X. Need not be all functions on that, because particularly if you give topology on X, then you can take continuous real valued functions. So L is a vector space of real valued of some real valued functions. Need not be all. Defined on X, so vector space, such that so that you have the notation. These are functions. Such that you have, look, if you have functions, so usual order is there already. That I already told you. This will mean if fx less than equal to gx for all x belongs to x. This will be the usual order. When you take a collection of functions to form a vector space, if nothing is mentioned about the order, partial order, we take this order. That's the usual partial order on the functions. Okay, and as I checked that before, it will be a partially ordered vector space, That will L with this scalar multiplication and this order, it will be a ordered vector space. And suppose since ordered vector space I have order, I can think about whether it is lattice or not. So if it is a lattice, that means any two elements, that's the thing. Given any two elements, you have both exist here. Exist here where? Are in L. Given any fg belongs to L, so in exists in L. Okay, that means L is a lattice as well. So if L is a vector lattice, so that means it will be called a function space if it is a vector lattice consisting of functions, real valued functions on a non-empty set. Then it is called a function space. Okay, basically it is a vector lattice, but since I am talking about function space, it consists of functions, real valued functions defined in a non-empty set. Okay. Now, since it's a vector lattice, you can prove that f plus. Now, if you have, so you have f plus, f minus. Here you can check that f plus x will be pointwise max. That is so. And f minus x is the max of minus fx here. Okay. Basically, it's the same function. Pointwise I am defining. So actually, I am taking these two functions. 0 is the constant 0 function if you take. Constant 0 function. Constant 0 function. That means everywhere it takes 0. That is the 0 of the 0 vector of L. Okay. So this is basically, you have this. This 0 is the real 0. This 0 is the 0 vector of the of L. And this is, sorry, not inverse. Minus equal to look, that's the way we defined before. So we are following the same thing. Okay, and mod fx, you can check that mod f. Given f, this is a function. This is actually can check. This will be same as this. Because on the real line, if you have go for this mod fx will mean what? We look at this f plus x, f minus x. Okay, f plus x, f minus x. Okay, so you can check that. So that this actually will be and F will be this. So what is the advantage? Advantage is that often in analysis, particularly, we need to work with, first you need to work with the positive thing. It's a positive thing. Okay, so that we do a positive thing and then we combine this result or this result. Like measurability is also like that. Okay, in functionalism often it comes. Here I should mention in that there is a well-known journal, Positivity. Wherever you split into two parts like the positive part, Positivity. It's a journal in mathematics. It's a well-known journal. Actually, he has died. Ali Prantis is one of the founder of this journal. Okay, the Positivity. In Positivity, they publish only papers where you have some concept of positivity. If you don't have in your paper, you do not use any concept of positivity, that they won't accept. Okay, right? That positivity in mathematics, in analysis, is a big thing because that's the way we simplify the case. First, we handle the positive things and then we mix up the whole, for a common thing we come. Okay, now look here. The example is giving that here are some examples of function spaces. Look, remember that R to the power X, X is a non-empty set. R to the power X by the Cartesian product, remember that this is exactly means functions. Okay. Here you should remember that suppose you have each xi is non-empty and for all I belongs to I, that axiom of choice that I'll be using again. I'll have to define the arbitrary product of topological spaces and I not equal to phi. This means those functions from I to union xi conditions such that a phi belongs to xi. But if you suppose each xi is same as x, suppose, then you look, it doesn't matter, then this will be all, that means this will be function what? This will be function f I, these are all x, so it will come x. Automatically it will be fi xi because xi is x, so automatically it will be satisfied. Okay, this will be automatically satisfied if I take this. If I belongs to xi means if I belongs to x, but I am taking this function, so that is the thing is coming. Okay, so this is notation is okay, right? With I to the power x, because basically the idea is that concept that you are taking I x times product. Okay, so that is the notation here. Here, this is your index set. This is your this thing. Here each xi is actually R. Here each xi is R and I equal to x actually. So this you are getting. So R to the power x that I explained last semester is this collection of all functions. Okay. Similarly, so that is a function space. So particularly it is a vector lattice. Okay. Function space you should know that is a vector lattice, but it is a collection of functions. Vx, x is a non-empty set. It is a collection of all real valued bounded functions. That means but bounded. Okay. So look, Bx actually is a subset of, so it is vector sublattice of this function subspace of that. This is a function space, but this is a subset of this. Now on this, when you talk about Cx, you need topology. Suppose you give a topological space. You give topology on X. Then Cx Then Cx is also this. Okay, right? This is also a function space. Okay. Now I should be careful. CBX. CBX, of course, you have topology. Okay. That this is Cx intersection Bx. That means it is bounded as well as continuous. This is also a function space. Okay. So that CBX actually is a subset of Cx, subspace rather, vector subspace of Bx. So ultimately it is a subspace of R to the power x. Here I should point out P. If you look at Willard's book, he in CBX he is using this, not this. In fact, why is this? It is a matter of notation between difference in the notation between topologists and analysts. Topologists will prefer this notation, star. Willard has used this, an analyst they use this notation. But why topologists don't use it? Look, Cx is already a set, and suppose you give a topology on this tau, some topology, not this tau. Suppose tau prime. You give another, or you take altogether different thing. Suppose you give a topology on this. Somehow you define a topology on Cx now. But to define Cx, you need a topology on that. So forget about this now. But you need a topology here. But now suppose on this you give a topology. So it becomes a topological space. Then topologists, they write often this. To indicate on Cx, I have the topology sigma. Of course, sigma is defined, that definition is given. That's why they don't prefer. In fact, they also use B topologist for some topology. So that I should clear. This should be clear. When you are reading from a book, first see that whether you are reading a book on analysis, or rather written by analyst, or you are reading a book on topology written by a topologist. So some notations you should be careful. Okay. So sister X, but why analysts they don't use it sister X? When you do function analysis next semester, star, then analysts they use it for the dual space. Okay, that I will talk about now. Okay, I'm just going through. So the think about it. I'm coming after 5 minutes. Okay. So, hello. Now, look, something is not here that I want to talk about. Just to give an introduction on that. So that since I talked about topology and analysis, now where analysis and topology they converge. Hello, horse is there? Horse? Hello? I'm looking for horse. Horse नहीं.
No, sir.
क्यों? Horse नहीं है? Why?
Sir, sir, he is
Today
being
He is
onboarded
he
today.
onboarded.
joined or he didn't join today?
Sir, he is being onboarded today, इसलिए.
He is on what?
Sir, he is on the campus. He is being onboarded.
He is being onboarded. But then to again
Yes,
he should
sir.
have more reason to attend this class. For what he is doing? Hmm?
Sir, some official work.
अच्छा ठीक है. So सुनो. Now it is not in the book. But in fact, you won't be taught that general thing in next semester. But I am just giving a concept because since I am talking about vector space, vector lattice. Now look, I talked about vector space. Then I talked about ordered vector space. And then I talked about vector lattice. Okay. Now suppose I have just a vector space, not this thing. That instead of V, I am talking about X, suppose. Now, look, suppose I want to give a topology on this, but the word behavior topology should have, like suppose on the vector, it is a vector space, I have this, the topology. But actually, so that I want this topology to interact with the vector structure of this. Because if it doesn't interact, then I will study this tau separately, not with this. But interact with vector structures means vector addition and scalar multiplication. Now what it should mean? Now look, if you have this, now look, then if you have this, then x cross x, I have the product topology that I already defined. For a finite family of space, what will be the product topology? Here, u cross v, u v belongs to tau, will be a subbase. Is a subbase, sorry, base. Subbase I have not defined yet. I will define. Is a base for the product topology. On x cross x. Now the expectation is that I have this, so I have the product topology here. Product topology, you just write PR. So from this, I have this thing. U, V is here. X cross X. Here I have U plus V. It's a function. U, V, X cross X. I'm taking the product topology out that right now for the map it is not there. Okay. So this is a well-defined function. And what will be my expectation? If I want topology to be compatible with the vector structure, it has to be continuous. It need not be continuous. Suppose it is continuous. Suppose so this thing, x cross x. Okay. But actually, what will mean that I can give you simpler thing that what will mean by continuity. That means if you don't want to go to the product topology definition and that all these things, but it will mean, look here. Continuity, I can use basic open sets. Okay, so that means given any open set here, sorry. That means given any open set here, the neighborhood of that, given a neighborhood W of U plus V, there exist neighborhoods U and V of U and V respectively. That means U is the big U is the neighborhood of small u, big V is the neighborhood of small v, respectively. This going this, suppose this is a function. That means phi U cross V should be contained in this W. But phi U cross V means what? Look, it makes sense. It makes the vector space addition of two sets means U plus V means actually this collection of vectors U prime plus V prime. V prime belongs to U, V prime belongs to V. So this actually means, so instead of phi, I can write this thing. Such that U plus V this is small, this is not the big. Given a neighborhood of there exists neighborhood U and V of this such that this. Without talking about product topology. Some analysts often they don't talk about product topology, they give this condition. So that means basically whatever you do it, this means the vector addition and the topology they are compatible. Okay, right? So this is the thing. And now what about the scalar multiplication? Now look, scalar multiplication will mean what? So you have this. This is a vector space. I am doing over R, so ठीक है. So that look, here scalar multiplication is a function from here. Alpha x, this is going to alpha x. This is the scalar multiplication. So this is another function. Here you have the topology. Look, here you have the product topology. But the spaces are different. That doesn't matter. Same way will come. U will be open in R, V will be open in X, and E cross V will be a basic open set for this topology. So that means that way you can do it. So, but if you the way I have defined for the product topology, there is X cross X. Here you have the product topology on this. So same way you can do that. If you assume to be continuous. Or else without talking about topology on the product space, you can see that given a neighborhood W of alpha x in X, there exists a neighborhood U of alpha in R and a neighborhood V of X in X such that this look. That means you are having U cross V. Don't think about it. Here E cross V means what? So psi will actually be U phi. But if we make sure that what does it mean? It means alpha V prime. I'm just using that. There is a neighborhood V of X. Anyway, X. So I can take that. Alpha belongs to U. Scalar multiplication and V belongs to V. It's a notation. So that so you can take that. If with this notation, if you use it, so this is not a standard notation. This. Okay, right. Then you should explain that what is the notation means. It should have. That means if you have this, That means the topology on X is compatible with scalar multiplication. Suppose you have it. I need not have you have. I am telling you, like look in the R with usual topology. Because it's a metric topology. This is compatible. Look, by sequence you do fxn goes to x, yn goes to y, implies xn plus yn goes to x plus y. And if alpha n goes to alpha in R, and xn goes to x in R again in that, then implies alpha n xn goes to alpha x. But since the metric space continuity can be generalized, can be characterized through sequence, so this is here. So this is compatible. So this is you have here the topology is compatible with the vector structure is compatible. The vector structure of vector structure of R, usual vector structure. But on this, if you give discrete topology, this won't be not compatible. You can prove it, it is not difficult. Not compatible with the vector structure. So when you have a vector structure, it's not any topology you will consider. You will only consider topology basically. You consider topology if I want to study the vector space at the same time, which is compatible with that. That means you have X, you have this is a vector space. That means a linear space. And tau is a topology. I already explained what does it mean. Compatible. Willard has given this thing in the exercises. Compatible with the vector structure. That is vector addition and scalar multiplication. Compatible with the vector addition and scalar multiplication. Suppose you have it. Compatible means this thing function I told you. Vector addition, that is these two are continuous. These two are, I already told you that means what are continuous. It will come from the product space will come. Okay, one function will be this. Scalar field can be also complex in Jan, that doesn't matter, but here you take R. Okay, it can be to do that also. That I will tell you later. That here, because here I do not need any other than vector structure. I do not need any lattice and then so that these two functions. Here you have the product topology. These two are continuous. Look, since I'm taking vector structure, okay, right? So I could take any scalar field, okay. I could only that scalar field I will have to have some topology, but usually R or else if you take C, could take C because C you have the usual topology like R. If you take any scalar field, then I'll have to say what is the topology there. But R and C they have the usual topology that we consider. So that here you should understand that if I take vector space over real, it is called a real vector space. If I take real vector space, the scalar field is real, and if I take real scalar field complex, then it is complex vector space. Okay, Now, all these things which I discussed with this all can be discussed with C also. Now you see, in function analysis, do not take usually vector space over anything. We take either real vector space or complex vector space, so that we know what is the usual topology there. Okay, and we take usual topology there. In function analysis, we take spaces comes. First of all, vector space comes. That will be either real or complex. And a topology will come which is compatible. That means vector addition and scalar multiplication are continuous. Then this will be called, here the scalar field you could take C also. Called, look, here is a vector space and you are giving topology, but they are compatible. It's called topological vector space. That's why I've taken so much time, because since I was talking about topology and vector space, so I came with this topological vector space and TVS. Some people write TVS, topological vectors. Some people use this prefix, then they call it linear topological space. Linear, but same thing, linear topological space. LTS. It depends on the taste of the author. But they're same thing. Topological vector space, linear topological space. It means on a vector space over R or C, this is clear. You have a topology which is compatible with respect to the vector structure of X. That means both the vector addition and scalar multiplication are continuous. Now look, I'm just giving you this. In function analysis, what will we do? You will study next semester a very special kind of this thing. You won't be taught general thing. Special kind of TVS. That I want to explain. Special kind of TVS. Okay. In fact, function analysis has many branches, and particularly who got topological vector space study and that only. That is called topological function analysis, because there they use a lot of topology, the topological function analysis. Now look, I said special kind of TVS. Now here after topology, you are doing topology now. Last semester you did metric space, but you can see if you have topological spaces, among topological spaces, probably the metric spaces are the nicest. Because the metric space you don't particularly why nicest, because many things you can characterize through sequences. Okay, through sequences. Now I just want to explain that, then I will take class on Friday. Now among these topological vector spaces, the nicest space probably is called non-linear space. It is special kind of metric space. That's the good thing. It's a metric space. So you can only need to know the metric topology. What is a nonlinear space? Here, look, model is R. Look, here, given X belongs to R, you got this mod X. And the function, look, metric D, usual metric, you got this what? Basically, which is distance from 0 to X minus Y. Basically, you need to consider one vector. You think about this, one vector. So basically, you need a concept of distance from 0. Now look, if you have a vector space, you have the concept of 0. So suppose I generalize this. Here, if you generalize this, first of all, you see that what you get. You get this. If and only if X is 0 vector. You get this. Though it is alpha another real over time taking, this is can be written as this. And sorry, using already the notation in that. And you have this so-called triangle inequality. In fact, in order to define the metric topology, you needed only these three things, nothing else you needed. And that tells you that here the vector addition is scalar multiplication continuous. That means if xn goes to x, yn goes to y, implies xn plus yn. You have used triangle inequality here. Yn goes to x plus y. Similarly, if you have alpha n goes to alpha, xn goes to x, implies alpha n, xn goes to alpha x. You will use triangle inequality, but you will need something more. Okay. Now suppose this I generalize. Then what will mean that? That means, sorry. Suppose I have the vector space over F where function analysis, the scalar field is only R or C, because on that also you need topology. F is, but once you fix a scalar field, you don't change it. That means either you take a real vector space or complex vector space. But after choosing, you don't mix up, because every complex vector space is a real vector space. You don't have the choice of that. But a real vector space need not be a complex vector space. So suppose you have this. Now look, suppose I have a function like this, phi x to, look what I'm doing, r plus. R plus means non-negative reals. What is this function? Look, remember that mod x, this is a non-negative function. So I am already saying this. Okay, suppose this. So 1, remember that if and only if x is, look, this x is 0 means 0 vector. This is scalar 0. So phi x is 0 if and only if x is 0. This is 0 vector. This is scalar 0. 2 phi alpha x. Look, I have got. This is the distance. Sorry, this is the distance. This is alpha. So here phi alpha x is coming phi of x. Okay. So this is for the scalar. That's absolute value. I'm keeping it separate. So here it will be. Suppose you have it. Okay. You should write for all alpha belongs to f and for all x belongs to x. Okay. And third, so triangle inequality. How will it look like? That phi x plus y is this. Suppose you have this, these three things. Suppose you have it. You don't need to have. You have it. On R, Rn, I have this with the usual topology, with the usual distance. Even in Cn also, the usual distance. It's not something I don't have it. I have it. Okay, a vector space. Only thing that vector space may be infinite dimensional also. Now look, you have this. Then I said phi doesn't look like a good notation, because we are having this thing here. Okay, that's why we do not use that. Suppose in place of phi, use this notation, yan. 2 lines each, vertical lines. Okay, right? Suppose you use it. That means instead of this, that means this is a function. Look, mod, it was a function from R to R plus, non-negative reals. This was a function satisfying these things. So here, if I use this notation, then how it look like? Now look, to look like the real word you're getting there. Okay, and it will look like what? Now look. Sorry. And here. See, guy, I'm doing this thing only. Only I am taking two vertical bars. And this one will look like what? should have written here. I didn't write, forgot. Or all xy belongs to. Okay. Look, suppose I have it. I have RNC and I have examples. I will give you better examples also. Not necessarily finite dimension, infinite dimension. But like, look, I am just copying this, but with a different notation. Suppose you have it. You can check if you have this. I said, I have not checked whether vector addition, scalar multiplication, they're compatible with the whatever. First, but I have not yet to finish the talk on that. So what is this? Suppose you have it, okay? Suppose you have it. Now, no immediate thing you can do, I can define a metric on that. Look, what I'll do, like what I did for the real line, I'll define. So you define. Okay. I'm teaching you something which you will learn in the next semester, but something topological linear space I talked, I am giving in trying to give you the simplest example of topological linear. And you can check T is a metric on X. And this is called a norm on X. So you give a metric topology and you can easily check this metric topology. So you can have the sequential characterization. Here you can check that, look, that vector addition and scalar multiplication, they are continuous. Okay. Now that means what? Now look, basically you need to check, here you have got this. So if you have this, what will mean is metric topology, means goes to 0, goes to this in xt. Look, if and only if you have this. Look, dxn x means this. If and only if, so this. Okay. So with this you can prove that if xn goes to x, yn goes to y. Now once you have it, we write instead of this. We don't write this because this tells you something linear structure also and gives you the metric topology. D is induced by this norm. This is called a norm. And this couple is called a normed linear space. Normed linear space or normed vector space. Okay. Normed linear space or normed vector space. Okay. Norm means I'm realizing what you have this. Then you can easily prove that it implies an alpha n scalar in F and xn goes to x. This is x. The metric topology, this is in x, implies xn plus yn goes to x plus y, alpha n xn goes to alpha x. You can prove like way you proved in real line if you know the proof in x. So that will tell you this is vector addition and scalar multiplication, they are compatible. If you have this, then this is called a norm, this is called a non-linear space. So that actually it is a topological linear space. This is the probably the finest example of topological linear space, the easiest to handle. Okay, like metric space among all topological spaces. So you have this non-linear space. Okay. Both another 5 minutes. So I talked about non-linear space. Linear space on which you have a norm, whichever norm automatically will ensure this. Like real line, I have not changed much the idea. So that I have not changed the idea much. So that automatically it will give you this. If you have norm, it will give a metric. Topology will be the metric topology. Now you see that. Don't confuse with that x. So x is a non-empty set, and you take bx. The whole thing I have done before here and I have done in the last semester. To take the linear space, vector space, of all real valued, could take complex valued also, bounded functions. On X. Remember, here I have defined the supremum metric. I called it uniform metric because this gives a uniform convergence. Yeah, now we look in the Aliplansberg, so they are talking about pointwise convergence, uniform convergence. DFG, I defined this. Okay, right? It's a linear space. But look, this D I could get if I define this. This is called the infinite, suppose. Look, I have taken bounded functions. So this is a real number. Because this is bounded. And you can check, verify. Is a norm on Vx. So that means Bx, this is a nonlinear space. Is a nonlinear space. Often we do not write the norm separately. Often we write this. This tells you that I am taking this norm. This norm is called because look now DFG. What is DFG now? Now look, DFG, you have taken this. But that nothing but by the definition, this is this. And that's the way from norm I am giving the metric. Remember in a metric, don't confuse that is. If you have a nonlinear space, then dxy was defined. Here that I am taking this norm, this. And the big metric D, it is big D. This I have this. Okay, so this is giving the metric induced by that. So that this is a, that means now you see, actually we are considering this nonlinear space for that. And this norm is called infinity norm. Because we are using notation infinity norm. We are using through supremum, it is called different name, supremum norm, sup norm, or uniform norm, because it gives you uniform convergence. Uniform norm. These are just different names of the same norm. Okay, right? Now remember that just one thing. Nonlinear space is a metric space. But I told you, given a metric space, your first concern should be whether it's a complete metric space or not. Here is the functionality is more important. Complete metric space. So that means given a nonlinear space, my first question would be whether it is a complete nonlinear space. Complete nonlinear space. So that's a special thing. And a complete nonlinear space is the definition. A complete nonlinear space is called, it is an honor of Banach because he was one of the founders of function. It's called a Banach space. Stefan Banach. In fact, next is the functionality. All the time you will hear of Banach space. Okay. Here also you will see that what is the importance of completeness, because Bayes category theorem. Because only on a complete metric space you can apply. You can be sure of applying Bayes category theorem. Okay. And here, so that a complete nonlinear space is called a Banach space. And here I should tell you that I am going to finish it now. I need to tell you that In function analysis, the cornerstones that can be generalized for the topological vector spaces also, but you will be studying nonlinear space. But if you can do well in nonlinear space, you can understand nonlinear space, you will understand topological vector space better. In fact, in order to understand topology well, you need to understand metric topology better. Similarly, for if you want to understand topological vector spaces, first you need to understand nonlinear spaces well. Okay, and a Banach space. In now function analysis, there are four cornerstone theorems, and let me tell you that Banach theorems. This is Banach theorem, one theorem, but people sometimes write plural. That I will tell you that one. Then you have that PUB, that means principle of uniform boundedness. These are the big theorems, and if you know them well, only then you can be good in function analysis. PUB, and open map theorem, closed graph theorem. Open map already I told you that in topology, homeomorphism, closed graph theorem. Graph. I have given you a question in minor. Be careful. The closed graph plays a big role in function analysis. That's why I have given you that question. Closed graph theorem. Closed graph theorem. Now look, these three theorems in the proofs use this thing. The proofs of this, in fact, it can be shown if your nonlinear space is not a Baird space, particularly is not a Banach space, it may not hold. Okay, that's why the importance of Banach space. If you have Banach space, your spaces, range and domain, almost blindly you can apply the theorems. But if it is not Banach space, one of them, then be careful. Okay, right? So this thing, because of this, make sure that you read the last question of 36, I think, of minor. So what does it mean closed graph and that? Okay, so only Hanmanach doesn't use this Bayes category theorem. Here I should explain that what is this S, why it is plural singular. Actually, original Hanmanach theorem, you can say that's a proposition or a lemma, original Hanmanach theorem. But Hanmanach theorem gives a lot of corollaries, The original Hanmanach theorem gives a lot of corollaries. In fact, while applying, we do not apply that Hanmanach theorem. We apply one of these corollaries. In fact, Hanmanach theorem together with this family of corollaries called Hanmanach theorems. People prefer to call them Hanmanach theorems. And in fact, when you apply one of those corollaries, you just say by Hanmanach theorem or by a corollary to Hanmanach theorem. You don't need to specify which corollary. People will understand, because you can't give the name by corollary 1, 2, 3, 4 because it depends on the author. How many corollaries they are having and how they are numbering. So you can, at best, you can say by a corollary to Hanmanach theorem. I get this. That exactly we do it. And that's why it's called Hanmanach theorems. Okay, because Hanmanach theorems, when you say, that means original Hanmanach theorem plus a lot of corollaries coming from Hanmanach theorem. Okay, so that I'm closing this class and I will meet you on Friday. But I am telling you that today what I taught, we just go to the definition of nonlinear space. And this. Now look, with this CBX, when you have a topology here, topological space, this is a continuous bounded functions. I can give the same norm because it will be a subspace of this. Actually, in function analysis, this is important. This is also important because when x equal to n with the discrete topology, this gives you L infinity. L infinity plays a big role in function. And this is in YAN, CBX, bounded continuous bounded functions. On this you are giving this. This is important. So that you read nonlinear space particular and then you read this because I am coming back. I proved last semester only so that I only mention these two results here. तालिप्लन इस बर्किन सर they have given. So see you on Friday. आज बहुत पढ़ा दिया तुमको. ठीक है. Where is this Sanju Wala? Huh? Is he there in the class? Hello? 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 Nobody is there. Hello?
Yes, sir.
Yes, sir.
जी संजू वाला कहाँ है? उसको लगता है हाईएस्ट मार्क्स मिलने के बाद अब पढ़ना नहीं है क्या? हाँ? एंड हर्ष को बताओ नेक्स्ट टाइम इन मेजर आई वांट फुल मार्क्स फ्रॉम हिम. ठीक है? ओके सी यू बाय फ्राइडे आई विल मीट यू. Topology.